Bash variables. In this video, we are going to see about bash variables. An essential feature of programming is the ability to use a name or a label to refer to some other quantity, such as a value or a command. This is commonly referred to as variables. Variables can be used at the very least to make code more readable for humans. However, variables really come into use in more advanced programming, when we are in a situation in which the actual values aren't known before executing a program. A variable acts as a placeholder that gets resolved upon actual execution time. For example, imagine that websites.txt contains a list of website addresses. The following routine reads each line, that is via cat, which isn't best practice but will do for now, into a for loop, which then downloads each URL. Environment variables. In this video, we are going to see about environment variables. Environment variables are available to the shell in which they are created and any subshells or processes spawned from that shell. They are often called global variables to differentiate them from local variables. By convention, environment variables are capitalized. Environment variables are variables that have been exported with the export built-in command. The shell in which a variable is created is called the parent shell. If a new shell is started from the parent shell, it is called the child shell. Environment variables are passed to any child process started from the shell where the environment variables were created. They are passed from parent to child to grandchild and so on, but not in the other direction. A child process can create an environment variable but cannot pass it back to its parent, only to its children. Some of the environment variables such as home, log name, path and shell are set before you log on by the /bin/login program. Normally, environment variables are defined and stored in the bash profile file in the user's home directory. A list of environment variables. Bash environment variables. Setting environment variables. To set environment variables, the export command is used either after assigning a value or when the variable is set. The declare built-in, given the X option, will do the same. Do not use the dollar on a variable when exporting it. The term environment variable. In this video, we are going to see about the term environment variable. The environment variable term contains an identifier for the text window's capabilities. You can get a detailed list of these capabilities by using the infocmp command using man5 term info as a reference. When producing text with embedded color directives, message cat looks at the term variable. Text windows today typically support at least 8 colors. Often, however, the text window supports 16 or more colors, even though the term variable is set to an identifier denoting only 8 supported colors. It can be worth setting the term variable to a different value in these cases. Xterm. Xterm is in most cases built with support for 16 colors. It can also be built with support for 88 or 256 colors, but not both. You can try to set term to either Xterm 16 color, Xterm 88 color, or Xterm 256 color. RxVT. RxVT is often built with support for 16 colors. You can try to set term to RxVT 16 color. Console. Console 2 is often built with support for 16 colors. You can try to set term to console 16 color or Xterm 16 color. After setting term, you can verify it by invoking message_cat color is equal to test and seeing whether the output looks like a reasonable color map. The path environment variable. In this video, we are going to see about the path environment variable. The execvp and execlp functions allow us to specify just the name of the file to be executed. These functions make use of the path environment variable to search for the file. The path value for a login shell is set by system void and user-specific shell startup scripts. Since a child process inherits a copy of its parent's environment variables, each process that the shell creates to execute a command inherits a copy of the shell's path. The directory path name specified in path can be either absolute, that is, commencing with an initial, or relative. A relative path name is interpreted with respect to the current working directory of the calling process. If the path variable is not defined, then execvp and execlp assume a default path list of :user/bin:\bin. As a security measure, the superuser account, that is root, is normally set up so that the current working directory is excluded from path. This prevents root from accidentally executing a file from the current working directory, that is, which may have been deliberately placed there by a malicious user with the same name as a standard command or with a name that is misspelling of a common command, example, si instead of ls. In some Linux distributions, the default value for path also excludes the current working directory for unprivileged users. We assume such a path definition in all of the shell session logs, which is why we always prefix // to the names of programs executed from the current working directory. The execvp and execlp functions search for the file name in each of the directories named in path, starting from the beginning of the list and continuing until a file with the given name is successfully exceeded. Using the path environment variable in this way is useful if we don't know the runtime location of an executable file or don't want to create a hard-coded dependency on that location. The use of execvp and execlp in set user ID or set group ID programs should be avoided or at least approached with great caution. In particular, the path environment variable should be carefully controlled to prevent the executing of a malicious program. In practice, this means that the application should override any previously defined path value with the known secure directory list. Some common variables. In this video, we are going to see about some common variable. We may encounter many common environment variables on system. We can find out how environment variables are configured by typing environment. This command is used to run a program with a changed set of environment variables, but when it is typed alone, it returns all the environment variables that are currently set in a format similar to that of bash environment variable assignments. Of course, the variables we see and their values will be unique to the system and even account. That's the whole point of environment variables. Variables we may see in this output include the following. User. This is current username. It is a variable that's maintained by the system. PWD. This is the present working directory. The environment variable is maintained by the system. Programs may use it to search for files when we don't provide a complete path name. Hostname. This is the current TCP or IP hostname of the computer. Path. This is an unusually important environment variable. It sets the path for a session, which is a delimited list of directories in which Linux searches for executable programs when we type a program name. For instance, if path is /bin:/user/bin and we type is, Linux looks for an executable program called is in /bin and /user/bin. If the command we type isn't on the path, Linux responds with a command not found error. The path variable is typically built up in several configuration files such as /etc/profile and the .bashrc file in the user's home directory. LD library path. A few programs use this environment variable to indicate directories in which library files may be found. It works much like path. PS1. This is the default prompt in Bash. It generally includes variables of its own, such as /u for the username, /h for the host name, and /w for the current working directory. This value is frequently set in /etc/profile, but it is often overridden by users. NNTP server. Some Usenet news reader programs use this environment variable to specify the name of the news server system. This value might be set in /etc/profile or in the user's configuration files. Term. This variable is the name of the current terminal type. To move a text mode cursor and display text effects for programs like text mode editors, Linux has to know what commands the terminal supports. The term environment variable specifies the terminal in use, which is combined with information from additional files to provide terminal-specific code information. term is normally set automatically at login, but in some cases we may need to change it. Display. This variable identifies the display used by X. It's usually 0.0, which means the first, that is numbered from 0, display on the current computer. This value is set automatically when we log in, but we may change it if necessary. We can run multiple X sessions on one computer, in which case each one gets a different display number. For instance, :0.0 for the first session and :1.0 for the second. Aliases. In this video we are going to see about aliases. An alias is the bash user defined abbreviation for a command. Aliases are useful if a command has a number of options and arguments or the syntax is difficult to remember. Aliases set at the command line are not inherited by subshells. Aliases are normally set in the .bashrc file. Because the .bashrc is executed when a new shell is started, any aliases set there will be reset for the new shell. Aliases may also be passed into shell scripts, but will cause potential portability problems unless they are set directly within the script. Listing aliases. The alias built-in command lists all set aliases. Example. The alias is printed first, followed by the real command or commands it represents. Explanation. The alias command lists the alias, that is nickname for the command, and the real command the alias represents after the equal to sign. Creating aliases. The alias command is used to create an alias. The first argument is the name of the alias, the nickname for the command. The rest of the line consists of the command or commands that will be executed when the alias is executed. Example. Multiple commands are separated by a semicolon, and commands containing spaces and meta characters are surrounded by single quotes. How bash expands a command line. In this video we are going to see about how bash expands a command line. Each time you type a command line and press the enter key, bash performs several processes upon the text before it carries out your command. We have seen a couple of cases of how a symbol character sequence, for example asterisk, can have a lot of meaning to the shell. The process that makes this happen is called expansion. With expansion, you type something and it is expanded into something else before the shell acts upon it. That's pretty straightforward. Any argument passed to echoes gets displayed. Let's try another example. So what just happened? Why didn't echo print asterisk? As you recall from our work with wildcards, the asterisk character means match any characters in a file name. But what we didn't see in our original discussion was how the shell does that. The simple answer is that the shell expands the asterisk into something else. In this instance, the names of the files in the current working directory before the echo command is executed. When the enter key is pressed, the shell automatically expands any qualifying characters on the command line before the command is carried out, so the echo command never saw the asterisk, only its expanded result. Knowing this, we can see that echo behaved as expected. Preventing expansion. In this video, we are going to see about preventing expansion. The standard output of a command can be encapsulated, much like a value can be stored in a value and then expanded by the shell. This is known as command substitution from the bash documentation. Command substitution allows the output of a command to replace the command itself. Bash performs the expansion by executing command and replacing the command substitution with the standard output of the command with any trailing new lines deleted. Embedded new lines are not deleted, but they may be removed during word splitting. As an example, consider the sequence command, which will print a sequence of numbers starting from the first argument to the second argument. With command substitution, we can encapsulate the result of sequence 15 into a variable by enclosing the command with $, and pass it as an argument to another command. Variables and command expansion. When a command is replaced by its standard output, that output, presumably just text, can be assigned to a variable like any other value. Login versus non-login shell. In this video, we are going to see about login versus non-login shell. Shells in Unix are classified into two categories: login shell, subshell, that is non-login shell. Login shell is a shell where the user reaches on trying to log in to his account. This login shell, ksh or bash or tcsh or sh, is defined for the user at the time of user account creation. However, the login shell of an user can always be changed by the root user. Subshell or a non-login is a shell which is invoked from the login shell or from a different subshell by just typing the name of the shell. In fact, whenever a shell script is run, a subshell is opened internally and the script is run from the subshell. How to go to a subshell? Simple. From the current shell, if you want to go to a K shell, type ksh at the prompt. In the same way, one can switch to any shell by typing the name of the shell at the prompt. In other words, any shell opened from the login shell in the above manner is a subshell. How to find out whether the shell is a login shell or a non-login shell? Two environment variables are available to find or identify whether a shell is login or subshell. Login shell. Assuming the user is currently in his login shell, which is tcsh. In this case, both the variables are showing the same value. It is because the login shell and current shell are same in this case. Non-login shell. The user initially is in login shell tcsh and then switches to ksh. On switching to ksh, The $0 shows ksh, however, the shell variable still shows tcsh. Bash Startup Task Profile. In this video, we are going to see about Bash Startup Task Profile. Bash behaves differently according to which type of shell is running. If it is a login shell, it executes the code in the following files in this order: /etc/profile as set up by the system administrator, or maybe the person who wrote the shell package for your system. /.bash profile, and if that doesn't exist, bash executes the file /.bash login instead, as long as that does exist. If that doesn't exist either, it looks for /.profile and executes that if it exists. All these are files beginning with a dot in your home directory. Note that ls won't show them. You need to use lsa. Be particularly careful with /.profile if you use that file to contain bash code. It is executed by the Bourne shell and all its direct descendants such as ksh. Putting bash specific code in /.profile can cause problems. On the other hand, if you use lots of different shells, it can be quite useful to put common code in this single file. For example, setting up your path or cd path variables here and marking them for export is a task common to all those shells. If the shell is not a login shell but is interactive, bash executes the single file /.bashrc. It doesn't execute /etc/profile.bashprofile.bash login or .profile. Note that no startup file is ready by both login and non-login shells. If you want all interactive bash shells to run /.bashrc, you can put an appropriate command in /.bashprofile. The following makes bash execute the commands in your .bashrc. The first dot is actually a command that tells the shell to read the named file, that is here. The file is /.bashrc, like a startup file. That is, all code will be run inside the current shell instead of in a separate process. This is necessary for the shell to set options and variables. If the shell started a new process to read the file, that is, as it would for a shell script, the current shell wouldn't get your new setting. This command is called the dot command to avoid too many cryptic punctuation marks in the text. You can use the dot command to split your startup files if you like to keep things neat. For example, some people like to keep all their aliases in a separate file. Let's call the file /.bash aliases and insert the following lines into it. To execute those lines from /.bash aliases, you can put the following in both .bashrc and .bashprofile. That command executes all the lines in the file passed as the argument, typed them as input to the shell. Sometimes describe this as sourcing a file. Bash Startup Task, Bash RAC. In this video, we are going to see about Bash Startup Task, Bash RAC. Using Bash Startup files to perform a task or set anything for a given shell, we had to execute the needed commands in a shell. One of the main limitations to this approach is that the same configuration won't be available in a new shell. In a lot of cases, a user may want that whenever he or she launches a new shell, whereas instead a new customized configuration on top of the default configuration is available for use. For customizing Bash, 3 files are available in a user's home directory that gets executed by default whenever a user launches a new Bash. These files are bash rc, bash profile, and .bash logout. .bash rc. In a graphical system, mostly a non-login shell is used by a user. To run a non-login shell, we don't need the login credentials. Starting a shell in a graphical system provides a non-login shell. When a bash is invoked in a non-login mode, the /.bashrc file is invoked and the configuration available in it is executed and applied in any bash shell being launched. Settings that are needed in both the login and non-login shell are kept in the /.bashrc file. For example, on a Fedora 22 system default, the /.bashrc file looks as follows. Any addition done in /.bashrc will be reflected only to the current user's bash shell. We can see that the .bashrc file also checks whether the etc/bashrc file is available. If available, that gets executed too. The /etc/bashrc file contains configuration applied to a bash shell for all users, that is, system-wide. System admin can modify the /etc/bashrc file if any configuration needs to be applied to all users' bash shells. The file /etc/bashrc also looks into the script files available in /etc/profile.d, which can be confirmed by the following code snipped taken from the /etc/bashrc file. Bash exit task. In this video, we are going to see about bash exit task. Only Linux and Unix systems programs have the ability to pass a value to their parent process while they terminate. This value is called an exit code. Programs that are terminating or exiting use exit codes to tell the process that invoked it whether that program was successful or unsuccessful. For POSIX systems, that is such as Red Hat Enterprise Linux, the standard convention is for programs to exit with a 0 status code for success and a non-zero status code for failure. A status code of 1, this means the application exited with a failure. To understand exit codes a little better, let's write a quick little script that performs a successful task. This quick little shell script performs one task. It runs the touch command on the file /var/temp/file.txt. If that file exists, the touch command simply updates the access time on that file. If the file does not exist, the touch command will create it. Since /var/temp is a temporary directory with open permissions, this script, when executed as the vagrant user, should be successful. After executing the command, the exit code can be seen by using the bash special variable $? This variable is a special variable in the bash shell that can only be used to read the exit code of the last program executed. This variable is one of a few special variables in the bash shell that can only be read and never return. To see the exit status of our script, we can echo the value of $? To our screen. It looks like this script returned a 0 exit status. This means the script executed successfully and most likely updated or created the file /var/temp/file.txt. We can validate that the file was updated by performing an ls/la on the file itself. From the output of the ls command, it appears the file was updated or created recently. The preceding example shows what happens when a script is successful, but what about when the script is unsuccessful? With a modified version of the preceding script, we can easily see what happens when a script fails.